Hello, so my name is Ben Goodrich. I'm a PhD student at the University of Tennessee. The first thing I'd like to talk about here is just something I'd like to show some visualizations I've done with a Pong simulation using the arcade learning environment and kind of just give a research update about just with what I've been doing lately. And I guess the title I gave this is Why Value Updates Are Hard. But that's just a tentative title. Really, I just want to show some visualizations and kind of show what I've come up with. So, as I just said, we're doing the Pong simulation with the arcade learning environment. And what I'm going to show is just different parametric models for estimating the value function, the QSA function in reinforcement learning. And I'd like to kind of just visually show kind of why I found some seem to work better than others, and you can see there's a big difference in how they train and in what they do. So my hypothesis is that catastrophic forgetting is a big factor here, and it's probably the main thing that's at play. So just some visualization notes for how I'm visualizing this QSA function. It's a 5-dimensional function, so I visualized it by unfolding things. And I've built this by taking values from the game's memory, from the RAM on the Atari. I found all 5 of these values in the games in the RAM, and I've taken it, and that's what I give from as my state signal. So what I give it is the ball Y position, the player Y position, the ball X and Y velocity, and the ball X position, so where it's at. So just to explain how this works, one square is going to show the ball's Y position versus the player's Y position. This will be a heat map. So imagine this is a heat map, and you would just imagine in general that you'll probably see large values along the main diagonal. So you imagine it would be brighter along the diagonal so that the player is aligned with the ball. But I mean, it'll be more complicated than that. That actually isn't what we'll see, but that's just the first thought that come to mind. So I'm going to unfold it as a grid of these. Actually, this is an error. This should say ball X velocity, not ball Y velocity. So I forgot to fix that, but this will tell. So I'll have a grid of these, and it'll look kind of like this. And along this direction of the grid, that means the ball is moving over here. The ball is moving to the right, so it's moving towards the player, and over here the ball is moving towards the left, so it's moving towards the opponent. And the ball Y velocity is the vertical here, so down here the ball will be moving down right, here it'll be moving up right, here it'll just be moving right, it'll be moving horizontally, and up here it'll be moving up left, and you get the idea. Down there is down left. And so I have it unfolded again with the ball X position. So over here, the ball will be on the enemy side of the board, and this whole thing here shows the ball as it gets closer to the player's side. So that's kind of how the visualization will work. So let's just jump right to it here. Actually, wait a minute. So I should talk about what I'm going to show. I don't know if it should be readable. I'm going to have a tabular run I'll show. First of all, this just shows the performance profiles of each one of these runs. So the tabular run, so that's the first thing I'm going to show. It's a blue line. All of these train, other than the one of the neural networks, the green line. And it should be noted, it was really difficult for me to find the parameters to make these train properly. I had to do sometimes 500 runs or 700 runs, and only so many of them would train properly. So these are just the ones that manage to work. This should not be reflective of how well each one of these techniques perform, because some of these perform really poorly, and these are just the 1 or 2 run. I only wanted to show the ones that worked here. So actually, I would like to show later that the cluster select seems to perform best out of all of them, but these are just the ones that got lucky. So don't use this for a comparison. This is just for what I'm going to show. So let me jump right to it here. As you see here, the tabular case, this is the very first episode. It's just a table of values. So it just looks like noise, this heat map does at first, because it's uninitialized. Each pixel is like an entry in the table on this unfolded heat map. So I should talk about the intensity range, how this heat map works. So this is the palette below right here. It tells, so the darkest color, it corresponds to minus 0.001 if you see the intensity range, and the brightest color corresponds to 0.001. Now as I play this intensity range will change, so it'll try to match the actual min and max values in this whole display, so it automatically adjusts that. So the scale does change, and you'll see you can think of this intensity range as the scale of the graph, and you'll see it change. So as it plays out here, it'll show the total reward, the average reward. So and then some of the parameters are shown for this particular run. So I'm going to go ahead and hit play so we can watch this. And as you see there, the intensity changed. So the scale changed and it suddenly got bright. So as you can see, starting out, our agent's losing. So over here is those negative values for where it's getting the negative reward. If you remember, this is the player's side, so it's missing the ball and getting a negative score. Over here is the opponent's side. So the few times the player wins, these bright values show up, showing the player, successfully gained a score. So over time, this value function will propagate these bright values over to where they need to be, so it can decide which actions to choose. So these values get propagated. It happens very slowly. We're about 45 seconds in. I'm going to go ahead and skip it to about 2 minutes in just to see. So it skips ahead 2 minutes in. So you can see it changed. We're at episode 4000 now. So the average reward, it's still losing. So you see this reward. This was what you saw in the plot earlier, this average reward. So now the player's starting to win. And you see a bright value actually appeared right here, showing this is when the ball is on the player's side. The player kind of knows what to do because it's propagated that reward, the value. I guess you could say it's learned the value. So I'm going to jump ahead to 4 minutes. So that actually completely changed. So here, this is like a really it's a nice policy. It's the player scoring 19. So when in Pong, the player can score 21 and the opponent can score 21, and the reward is just the sum of the player's score minus the opponent's score. So here the player is winning almost every shot. So if I'm going to go ahead and skip to the end, I'd like to show some more stuff here. So this is actually towards the very end. I'll just pause it here. I'm going to switch to the next thing I want to show, which is the neural network run 1. So this is the one that failed, and actually most of them failed. So if I run say 500 of these with different hyperparameters, most of them are going to look like this one. So I'm going to skip ahead and show that one. So this one runs faster than the others just because I plotted fewer frames because it takes a long time to plot each frame. So as you can see, it's not just random noise on the first frame. It's a neural network. So even though it's uninitialized now, there's actually some shape you see. So I'm going to go ahead and play, and you'll see the shape change. And so here it's learning. Well, it's trying to learn. It's not really learning. As I just said, this one fails. So actually, this one isn't very interesting because it fails. And maybe it is though, because most of them do fail, and we'd like to know why. As you can see, the whole thing changes. Like the updates are global, so I think that. I don't know, but I think catastrophic forgetting. There's probably other reasons. So actually, I only tweaked the parameters very slightly from the one that didn't fail. The next one I'm going to show you, and I got this one. So this should still be a good run, because the one I'm going to show next is a good run, and I only made a slight tweak to how it behaves, and I got this behavior. So here it just sits here. It's already failed, so I guess the weights the parameters got in a poor location in the neural net, and there's just no way back out of this. It's failed. So it's converged to this failure state, and there's no way out. So if I skip ahead, this is what we see. So next, I'm going to show one that doesn't fail. And this is only, I'm not going to say what I did. It wasn't much. I changed some of the logic of how it does. Well, it's nothing important. I changed something to do with a bias neuron. I was kind of playing around, but it's not a big change. It's not a change that should affect very much. So here's one that works, and as you can see, it's learning the value function. We'll just watch it here for a minute. So it's still at minus 20 average reward, and so there's not much to say. You can see this doing its updates. I guess I'll skip ahead a little bit. So we're about 30 seconds in. Let's skip to 50 seconds in. You can see it kind of taking a shape, and yeah, so it's just interesting to see the overall shape of the output from what the neural network is how it learns. So I mean, yeah, I don't know, it's the updates could just be poor initial parameters, could mess it up, or it could be so my hypothesis is, well, actually it's winning now. So this one has, there may be some luck involved in this, but it seems to have learned a good policy, and you saw it, its average reward went down, now it's coming back up again. So I'm going to skip to 2 minutes in just to see what happens here. So it's hovering around 12 now. So now it's climbing back up. Actually, whoa, it just dropped. That was interesting. Let's see that again. So, okay, so it's at 14. I paused it. I'm going to play right now, and we can watch it drop. Watch how the value function changes. So there's something went unstable here. Watch this. So notice it. I see it getting darker. I can't interpret the shape well enough to see how it failed, but so we saw a failure there. Then it seems to recover from it, and so something happened there. Something got corrupt in this function, and it yeah, that's pretty much what happened. I'd like to show there's catastrophic forgetting involved, but I don't know that that's precisely what happened there. So here we have a radial basis function network, and I actually had really bad luck with these. I trained probably 900 or 1,000 of them, and this was and each one I trained had different hyperparameters. This is the only one that worked, so I'm playing this one. And I know other people, there's plenty of papers where people suggest using radial basis functions, and I'm sure they might work in other problem settings, but in this particular problem setting, this doesn't seem to work so great. So you can see the nice circles, so the shape of the value function, at least uninitialized, there's centroids here. I think I used 100 centroids. I've tried more and less. I've tried playing with the widths. That was another hyperparameter. So I've tried changing all of that stuff, and ran nearly 1,000 tries. And so I'm going to play this one, so you can see what it does. So we're about 1,000 episodes in now. So a radial basis network, you have the outputs of each neuron is just each hidden neuron is just distances to the centroids, and it's like Gaussian distance, so it's inverse distances, and you do linear regression on top of that. So it's learning via linear regression how to update the weights to those centroids. The centroids are fixed; they never move. So at least I'm just talking about how radial basis networks work. It's pretty straightforward. I recently had to implement it for this, so it's been on my mind. But here we see the average reward, so it seems to have learned. Now it kind of worked. I suspect there's a lot of luck involved in this, because remember, this is the one out of almost, I think I ran like 900 of these, so I think it just happened to find a shape that's kind of working. You notice the reward is only about 9 or 10. Actually, it just stopped, so that's the next fall. So the reward was it, so it doesn't work so great. And I'm going to go back to my plot of these here. So you can see the radial basis run, that's the green line. It only goes up to about 10 or 11, so it doesn't work extremely great. But it, and it's the only one that did anything at all. Most of them just flatline. They didn't learn anything. So I've had poor luck with this. And I think those centroid, like if you look at those circular centroid shapes, I think it has something to do with their shape. It's just difficult in this problem case for it to learn. And I know, like I said, other papers have done well with this. So anyway, the last thing I'm going to show is the best, I believe. I saved the best for last. It's a cluster select run, which is the technique I have of partitioning a neural net. Let's go ahead. I'll talk about it while it's playing. So I'm just going to go ahead and play it, and you can watch it. So this partitions a neural net into regions. So it's almost like each region gets its own subset of the neurons for each update, and that helps. That actually I've had, I mean, I'm partial because this is the technique we're working on, but I've had actually really good luck with it, at least in this test case, and also in a cart pole test case. But as you can see, like the shapes just form so naturally here. And although this is, I think I did 500 runs of these, and I had like a couple dozen that learned pretty well. So it seemed like it. I mean, I'm still trying to make comparisons. I'd like to do a write-up and show, but it seems like just preliminary. This seems like it does a great job of taking a shape, and I've had better luck with this than any of the others. So I mean, that's the point. This is kind of aimed at mitigating catastrophic forgetting. So I would like an update to one region not to affect other regions. Now, you see the whole thing flashing darker and brighter. I think that has to do with a bias neuron that's shared among all the neurons. So the update should be highly localized, though. So that's it. We're done. So I didn't make a conclusion slide, but if I were to make one, it would probably just be what I started with, that this is a hard thing. So a lot of things have to happen correctly to get a good value update, or to get for this to actually work. And yeah, it's a difficult problem, and I think I've shown through visualization just how some things look, and the research is still ongoing. So I'd like to implement a replay buffer, like they did with the Nature paper, for the paper that came out. So I believe I'm done. I'm going to stop it here. Stopping now.